Exercise 4b, question 6. The first part I've already laid out here, and essentially we had to find the Maclaurin series including the first three terms for f of x equals arctan x. Rather a lot of tedious differentiation had to take place, and you can see I've got that laid down here. So here we go, the first derivative, second, third derivative, fourth derivative, fifth derivative, and then I've simply evaluated these derivatives at 0 to give me these values here. Then over here you can see I've written down arctan x equals 0 plus 0x squared over 2 factorial minus 2x cubed over 3 factorial, etc. And eventually that's simplified down to give what we wanted, the arctan of x, the first three terms. Right, on to the next part. For the next part of the question we're asked to find the radius of convergence, and the textbook gave us the series as the summation from k equals 0 to infinity of minus 1 to the power of k, x to the 2k plus 1 over 2k plus 1. And if you check, you will find indeed that does give us the terms that we had previously for our arctan series. Okay, let's have a see what we're going to get then. We're going to take the ratio test, and essentially we're going to claim that this has to be less than 1 for convergence. So I've started out just by putting in your uk plus 1, and I've divided that by uk by multiplying just by this reciprocal here. I've tidied up a little bit, and now I'm going to simplify. Okay, let's subtract the powers of x first, and that will leave us with x squared. And then these are the two parts I will simply write down as 2 times by k plus 1 over 2k plus 3. Using the algebra of limits, I can bring the x squared like so, and then say the limit k approaching infinity of the quotient 2k plus 1, 2k plus 3, and what we essentially require for convergence is that that has to be less than 1. So that's for convergence. Okay, so we'll take this a little further. X squared, the limit as k approaches infinity, we'll divide throughout by k, which gives us 2 plus 1 over k over 2 plus 3 over k. Has to be less than 1. And it's very easy now to take this limit, and so as k approaches infinity, this is going to tend towards 2 plus 0 over 2 plus 0. That has to be less than 1, and we can see directly that that's true if x squared is less than 1, and that will lead us directly to that the modulus of x then must be less than 1 as desired. The last part of the question is really quite interesting. At first we might try and use the Lagrange error, which I've written down here, but immediately there is a problem. There's no clear way to write down the n plus 1th derivative of arctan of x. If we look again, however, we'll notice that the series that we've been given is an alternating series, and I've put down here what you should probably do now is go and read key point 3.8 from the textbook. What it essentially says though is this: imagine this situation here where Sn is the nth partial sum, Sn plus 1 is the nth plus 1 partial sum, and S is in fact the limit that this series is tending towards. Well, essentially, if we use Sn as an approximation for the summation of the series, we'll get an error which is equal to the magnitude of S minus Sn. I know it looks like it'd be Sn minus S here, but I've used the modular sign to be able to write it down this way. So that would give us the error in doing that, and all we're going to claim here is that error must be less than what you get if you take away these two terms here. So the modulus of Sn plus 1 minus Sn. And we can see that just by in fact looking at the diagram. Now the question is, what's the difference between the n plus 1th partial sum and the nth partial sum? And the answer is, if you picture it or if you write it down, it'll simply be the magnitude of the n plus 1th term. So what we now have is that the error that we incorporate by truncating a series will always be less than or equal to the magnitude of the next term. Now we can use this fact by saying that by truncating at the nth partial sum, the error that we get will be less than or equal to. So I'm actually going to write down that the error term that we get will be less than, not less than or equal to, actually just less than the magnitude of the n plus 1th term. And the magnitude of the n plus 1th term, we can forget about the minus 1 to the n plus 1, and we'll simply get x to the 2 times by n plus 1 plus 1 over 2 brackets n plus 1 plus 1, and that in itself tells us that the error will be less than x to the 2n plus 3 over 2n plus 3. Okay, now what we want to happen is for this error essentially to tend towards 0 in the limit as n approaches infinity. We can now look at this part here and we can note the following: that x to the 2n plus 3 over 2n plus 3 will always be less than, well, x is a value, as we showed in the previous part, such that its magnitude is less than 1, and a number less than 1 raised to any power will always be less than 1, so we can make this claim. And then furthermore we can see that it is always going to be positive, so we can make this claim, and then we can say by the squeeze theorem, because this will go towards, in the limit as n goes towards infinity, this will obviously go towards 0, this is squeezed in between, and therefore by the squeeze theorem we can say that the limit as n goes towards infinity of x to the 2n plus 3 over 2n plus 3 is in fact going to be equal to 0. So the error term will go towards 0 as n goes towards infinity, and therefore eventually we can conclude that the given series does indeed converge to give us the function arctan x.